Let us start. Let me introduce Assaf Hamo from Harvard University. Assaf did his BSc in Hebrew University, and then his master and PhD with Shahar Lilani at Weizmann Institute on electronic and mechanical interactions in one-dimensional nanosystems. And he then went on to postdoc with Amir Yacobi's group at Harvard University, where he's working on cryogenic scanning magnetometry using NV centers of diamond. He will talk today about some results of that work. He's also available for Zoom meetings during the next few days, but not too long because his wife is expecting next week. So I urge you all to schedule on Doodle meetings with him as soon as possible for Sunday and Monday. So without further ado, let me pass the microphone to Assaf, who will tell us about imaging hydrodynamic flow in tungsten telluride.
Yeah, so thank Asa. So today I want to tell a story about imaging of hydrodynamic flow in tungsten telluride. And the first question that comes in mind when you look on this title is, why would you like to do imaging in the first place? Because usually when we deal with condensed matter systems, what we do is we hook up wires, we apply currents, we measure potentials, and we apply electric and magnetic fields. And what we're trying to do is to figure out what is the basic physics underlying the behavior of the electrons in the system by looking on the response of the system to all those probes. And if you want, this is very much like having a box and some object inside, and we're trying to figure out what is inside this box by shaking the box, by tapping on it, by trying to hear what's going on inside, whereas sometimes it's actually make more sense to open up the box and take a look. And today I want to give you a nice example for that, how just imaging, how looking on the current inside tungsten telluride, in this case, tells you a lot about what's going on in the system, that the current is hydrodynamic and what are the origins for those hydrodynamic effects. So today's topic is liquid of electrons. As we all know, we have 3 phases of matter, and it turns out that you have very similar phases in electronic systems. So the most common one is that of a gas, and this happens when the kinetic energy of the electrons is larger than the interaction energy. And in that case, you can describe every electron as a free particle and the whole electronic system as a gas, also known as Fermi gas. The complete opposite extreme is that of a solid. And this happens when the interaction energy of between the electrons is larger than the kinetic energy. And at some point, it's actually beneficial, energetically favorable for the electrons to be localized and to form a crystal, also known as Wigner crystal. And finally, the liquid. The liquid is a bit more subtle. It has to do with the dynamics of those electrons. It turns out that when the interaction between the electrons are just rapid or fast enough, you can describe the flow of those electrons using fluid mechanics or electron hydrodynamics. And the reason I brought all those images is just to highlight the fact that a lot of what's going on here has to do with space. The signatures that those phases have has a lot to do with spatial signature. And the simplest example for that is, of course, the solid, because if you would be able to image how the electrons order themselves in that system, you immediately understand what's going on in the system. You will see that it's indeed a solid of electrons. So this was part of my PhD project, where we used a carbon nanotube as a host for Wigner crystal, and another carbon nanotube as a probe. And actually, at the beginning, it didn't work so well. We found out that the probe interacts too strongly with this crystal, and we found out that this can lead to all sorts of weird phenomena like attraction by Coulomb repulsion of the electrons. But after fine-tuning this interactions between the electrons and the probe, we were able to image this crystal of electrons, and this is what you see here. When you look on the density. So those images just represent the density of the electrons in the carbon nanotube. And now it's kind of clear, just by looking on that, you see that the electrons order themselves like beads on a wire or like crystal. So this is kind of going back to what I'm trying to say. Just by looking on what's going on in the system, you can immediately understand what's going on. Whereas just trying to measure with transport and try to understand if indeed the system is within a crystal or not, which we actually tried, it's much harder. You can have a lot of effects that will look the same in transport. But when you look on this image, it's kind of clear. So similarly, if you look on the liquid phase, a lot of what's going on in fluid mechanics is what you want to do is to try to confine your fluid or try to flow your fluid in different geometries. And what you ask is how this fluid will respond to those different geometries. And this is kind of the motivation why we were trying to image to see how the electrons flow inside our material. And from that, we were trying to understand what kind of fluid do we have. So
just a quick question. Yeah. In the image you showed, what was the color? In the image you showed from the science paper?
So this is a bit. So the color represents the number of electrons in the system. So this is the line here represent the change between the colors represents the change between the number of electrons. Between 0 and 1, between 2 and 3, between 1 and 2, between 2 and 3, and so on and so forth. So the color just represents the density of the electron in the system in energy scale, if you want. Is that enough, or it's kind of it's a whole measurement. If you want to discuss it, maybe we should kind of talk about it. And it's just to the reason I brought it is just to show that it's very easy to understand when you look on that. But when you
it's okay. I didn't ask how you measure it. Just ask what is measured here. What is the quantity?
So what measured here is the density of the electrons. This is a measurement that represents the density of the electrons in the carbon nanotube. Yeah.
The upper one.
All of them are measurements of 1 electron, 2 electrons.
No, the upper nanotube, the one that moves. I mean.
No, the lower one has the crystal in it. The upper one is a probe. So we use the probe to image the crystal.
So the color is the density of electrons in the upper nanotube?
In the lower nanotube.
In the lower nanotube. Okay.
Okay. So yeah, so how can you get this kind of phase, the liquid phase of electrons? So the problem with electrons is, unlike regular matter, electrons live in another material. They're living inside the lattice. And it turns out that in most cases, the interactions of the electrons are not interaction between the electrons themselves, but rather interaction with the lattice. This is the most common interactions of the electrons in a conductor. This can be in two different ways. In general, one interaction is interaction with impurities, imperfections in the lattice, or interaction with the vibrations of the lattice, also known as phonons. But in any case, this kind of interaction do not conserve momentum, in a sense that the whole electronic system just keep losing momentum to the underlying lattice. And in that case, the flow of those electrons is going to be diffusive and can be described using Ohm's law. And if you want to get hydrodynamic effect, you need to use those interactions, the interaction between the electrons. And if those interactions are just rapid or fast enough with respect to those interactions, you can approximate for some amount of time the behavior of the electrons as a momentum conserving one. And in that case, you can describe the flow of those electrons using fluid mechanics. So this is very nice because now you can get all sorts of unique flows patterns that you know from fluid mechanics. But the problem is, how can you get to this point where the interaction between the electrons are just strong enough?
And is it always a question about the interactions, or what about temperature? Can temperature be, does it need to be, I don't know what, arbitrarily low?
So I will talk I think, a lot about this temperature dependence of the interaction. But yeah, in general, it should depend on temperature.
Do you expect to see this viscous flow in hydrodynamic flow in low temperatures or intermediate temperatures?
So in general, it's going to be a kind of window of temperature, because both this interaction and this interaction are going to be strongly dependent on temperature in most cases. So so you need usually to find a window where this interaction is actually higher than this interaction, or like more faster or more rapid.
Mm-hmm. Okay.
Yeah, I will talk about specifically one of the main figures of one of the main results is actually measuring as a function of temperature.
By lattice, you also mean disorder, I guess, not.
Yeah. So yeah. Of course.
Okay.
Of course, and this does not depend on temperature. So you need to start with, usually, this is I just want to, in the next slide, to use very clean materials. This is kind of the key component for getting hydrodynamic effects. Yeah. So yeah. So in order to get interactions in the system, there's one, like a simple way to go, which is using two-dimensional materials, and kind of a nice example for that is graphene. So as was mentioned here, a lot of the problems when you want to get hydrodynamics in electrons is disorder, and the fact that graphene can be made extremely clean, meaning that you have almost no impurities in the system, allows you to reduce the interaction only to phonons. And because phonons has a strong dependence on temperature, the interaction between electron and phonon has strong dependence on temperature, it's possible to control this interaction. But the two other properties of graphene, the fact that it's two-dimensional and the fact that you have low density of electrons, can allow for strong Coulomb interaction in the system. So not only you can reduce the interaction with the lattice, you can also get strong interaction between the electrons. And this is possible using Coulomb. And in fact, it has been shown both in gallium arsenide and in graphene that you can get hydrodynamic effects of electrons. So this is very nice, but it's going, if it was just going to rely on Coulomb interaction, it's going to narrow the range of the available materials that is possible to use for hydrodynamic effects to a very limited amount of materials, only two-dimensional, extremely pure materials. And if you want, for instance, to combine hydrodynamic with other properties that we know from condensed matter, like conductivity that is not isotropic, conductivity that is different for different crystalline axes, and there are predictions that, for instance, if you combine hydrodynamic with this kind of effect, you get all sort of extremely non-trivial flow patterns that has to do with hydrodynamic. You can also combine hydrodynamic with topology, like well semi-metal. But a lot of that is going to be extremely hard because those materials, those semi-metals, can be definitely made clean. This is an advance in a recent progress in material growth in recent years that allow for extremely pure semi-metals. But the problem is that those materials are not low dimensional and doesn't have low density of electrons. So you do not expect, in general, to get very strong Coulomb interactions in those systems. So it's unclear how would you get hydrodynamic effects in those semi-metals, in those clean semi-metals. Yet there are some signatures that you for hydrodynamic effect in those semi-metals, in palladium cobaltite, in a tungsten phosphide. Just using transport, they have shown that you get non-ohmic behavior of those of the flow of the electrons in those systems. So again, it's unclear how would you get those effects where in general you shouldn't expect to get very strong Coulomb interactions in the system. And what I want to kind of argue today is that there is a different way, different path for having interactions in such system that will allow hydrodynamic in those materials. And this hopefully will open the way to combine hydrodynamic with different properties and allow for those unique combinations. So the material that I want to show today is tungsten telluride. This is extremely interesting material. It has a lot of unique properties. In the bulk, it has been shown to be to have a giant magnetic resistance, predicted to be type 2 wild semimetal. In a single layer, it has been shown to be superconductor and quantum spin Hall insulator. And now, following a hint by a collaborator, that told us that he saw some transport signatures of hydrodynamic, we're starting to think how it will be possible to image to see if indeed the current inside tungsten telluride is hydrodynamic. So it turns out that you can do the simplest experiment that you can imagine, just trying to flow this current inside a narrow channel. And if this current, so made out of tungsten telluride, so if this current is non-hydrodynamic, this current should be just uniform along all the channel. But if this current is hydrodynamic, so following what we know from fluid mechanics, the current should avoid the edges and flow more in the center, following what is known as Poisson flow. So now it's kind of clear. All we need to do is to image this current to see if it looks like that or like that, and we can immediately tell what's going on in the system. Now, a simple way to image currents, or like the most direct way to image current, will be to measure the magnetic field that this current is generated. The thing is that the currents and the magnetic fields that are generated through Biot-Savart law are going to be extremely small. So you need extremely sensitive magnetometer, and also the relevant dimensions of this channel in order to those hydrodynamic effects to be available are kind of small dimensions. So you need micron scale devices. So you need also very high resolution. You need very high sensitivity together with the very high resolution. And in order to get that, we are going to use NV center in diamond. So NV center in diamond is an atomic defect in diamond that's made out of nitrogen and a nearby vacancy. And it turns out that the ground state level of this qubit of this atomic defect form a qubit. So you have a 0 state that does not depend on magnetic field, and 1 state that does depend on magnetic field, following Zeeman split. And the nice thing about this level spacing is that it's on the microwave range, in a few gigahertz, which allow us to control the state of this qubit using just simple microwave pulses. And to read out and to initialize this qubit, we are using optical pulses. We shine green laser, and those states are going to fluoresce depending on the state of this qubit. So if you're in the 0 state, it's going to fluoresce a lot of red photons. If you are in 1 state, it's going to fluoresce less. So this is kind of a way to read out the state of this qubit. And finally, the workable range in temperature of this qubit is extremely wide. You can work up to a very high temperature and down to a very low temperature. So now we have a qubit that is sensitive to magnetic field. You can control it, you can read out, you can initialize. So you can use quantum techniques to measure magnetic fields. You can use DC techniques, like Ramsey measurement, to generate superposition of 0 and 1 states, and just let it evolve. And because the 1 state depends on magnetic field, it's going to acquire some phase that depends both on the magnetic field and the time that you wait. So the longer you wait, the more phase you acquire, the more signal you have. So you want to wait as long as possible, but there is a limit. Of course, this is the coherence time, the DC coherence time of this qubit, which for NV center, it's about 1 microsecond, which limits your sensitivity to about 1 microtesla per square hertz. This is already very good, but you can get better. You can get better by filtering out the DC noise in the system and use AC techniques, echo measurements that will allow you to get sensitivities, coherence time of hundreds of microseconds and sensitivities of tens of nanotesla per square root hertz. And now you have kind of extremely sensitive magnetometer that will allow us to measure those minute magnetic fields that are generated by the device that we want to measure. Okay, but you have now a diamond, you have an NV center inside you need a way to bring this NV center into a close proximity of your sample. So in order to do that, we are going to shape the diamond into a sharp tip, and on the edge of this tip, we are going to have a single NV center. And the way it's done is following. You start with a plain diamond, you implant NV center inside, and then you're just going to etch this diamond into many pillars. And statistically, few of those pillars, and of course depends on the density of the implanted NVs, statistically we will have some pillars that will contain exactly one NV center inside. And now what you can do is to take this diamond with a pillar on the edge of it, and on the edge of this pillar you have a single NV center. You glue this diamond into a quartz rod, you glue this quartz rod into a tuning fork, and now using AFM techniques, you actually feedback on the frequency of this tuning fork, you can bring your tip with the NV center inside into a very close proximity of your sample. So because NV center is an atomic defect, all that matters in terms of resolution is just the distance of this NV center from your sample. So with this technique, we can get as close as few tens of nanometers away. In this work, it's about 50 nanometer away distance between our NV and the sample. And now, in order to move and to scan around this NV center above our sample, we need to use this microscope, a home-built microscope that will allow us to move and to scan this sample with respect to the tip, and also to focus the green laser on the NV center and to collect back the photons, the red photons that the NV center emits. And all of that is sitting inside a cryostat, and in a variable temperature cryostat, which allow us to control very nicely the temperature of the sample and the tip. And finally, a magnet that will allow us to control the levels of the NV center. Now, all of that ends up in the following image. You have an NV center on the edge of diamond tip, about 50 nanometer. The NV center is about 50 nanometer above our sample. And now what we can do is to scan our NV center with the tip above our sample and measure the magnetic field that is generated from the currents inside the tungsten telluride. Now, as I was saying before, what we want to measure is actually the current profile of this that is flowing inside the tungsten telluride. But what we are actually measuring is the magnetic field generated by those currents. So in order to understand, so first we want to understand what are the relations between the currents profile and the magnetic field profile. So let's take a simple example, just the current inside a gold contact. So in gold, we shouldn't expect to get any hydrodynamic effect, just simple ohmic current. So it's going to be what you see here, just uniform current along the gold contact. And if you calculate what will be the magnetic field profile following Biot-Savart law, it will look like that. Okay, so it's very similar, but it's a bit more rounded. It's not as crisp as the current, and this is because we are about 15 nanometer above the sample, above the gold contact, and this will result in kind of resolution effect. So now what about the current inside the tungsten telluride? So as I was saying before, because of hydrodynamic effect, the current should avoid the edges and flow more in the center. And it turns out the magnetic field follows kind of the same trend. It's going to be higher on the center and avoiding the edges on the sides. And now, all we need to do is just to measure the magnetic field above the gold contact and to measure the magnetic field above tungsten and telluride, and we can immediately understand what's going on in the system, if it's indeed hydrodynamic or not. So this is what we did.
This bar, what are the dimensions of this 1D system?
About 1.5 micron.
Well, how thick is it?
It's about 60 nanometer. So it's a finer thickness material.
How many layers is it?
It's about one, like it's 2 layers per nanometer, so it's about 120, something like that. Yeah.
So, and this tungsten telluride doesn't have any interesting surface states that kind of.
So it's unknown. I think it's under debate. There are some measurements using Josephson junctions, so just connecting superconductors to this tungsten telluride and reconstruct using the Fraunhofer pattern the flow. So people have shown some signatures of currents flowing in the edges, but we haven't seen that. So I don't know. It's a good question. There are some signatures that there are edge currents, but there are signatures that so maybe there are, but they are very small. I don't know.
Did you?
This is a measurement done in DC?
In singular, we know that in singular there are edge currents, I think. Yeah. What did you ask? Sorry.
This measurement is done in DC?
No. This is important. This was done in AC, because as I was saying before, our sensitivity for DC measurement is about 1 microtesla, and what you can see here is the magnetic field is few microtesla, and you see the signal to noise. Yeah, so here it's kind of easy to do AC measurement. You just apply current in one side and the other side, and then simultaneously or synchronizing with the echo.
And what is the frequency of this?
So specifically, this was done in about 50 kilohertz, like 20 microsecond cycle.
So what are the different experimental plots that you're showing?
Again, I didn't understand your question.
On the right, you're showing experimental plots. Is that right?
Yeah.
What are the different lines again? So the blue is the gold, and the red is the.
Yeah, the blue is the magnetic field above the gold. Sorry, the blue is the magnetic field above the gold, and the red is a magnetic field above the tungsten telluride.
So does this prove the point or does not?
So we think it is.
Well, I mean, they both kind of look, I don't know, the same.
Yeah, but you need to understand that the integral is the same, and actually the same exact dimension. The way we fabricate this gold contact is the same exact dimensions of the tungsten telluride. And if the current was completely ohmic inside the tungsten telluride, it just should look the same because the geometry is the same.
For example, gold has surface states. Can this just be the effect of some surface states of the gold?
Yeah. So those are very good questions. So exactly because of that, we're trying to think if this is indeed a real effect that has to do with interactions or not. And this related to your first question, because we know that interactions can be controlled using temperature. And the idea was to change the temperature and to see if indeed this is a real effect that is going to be changed as a function of temperature, or it's just something to do with geometry or something like that, as you were saying. Exactly. Yeah. So this is just the next slide. So this was measured in a specific temperature, 20 Kelvin. Yeah. So So what we did is we changed the temperature. We just scanned the magnetic field above the tungsten telluride for different temperatures. And this is this measurement here. So x-axis is the position of the enemy center, y-axis are the different temperatures, and the color just represents the magnetic field. So this kind of a complex figure, I want to start with simple 1D cuts of this figure. So you can look on 90-degree cuts. And again, it's the same, very similar to what I've shown before. And now what we can do is we can go to a lower temperature, to 20 Kelvin. And what you see is a very similar effect to what we saw before when we compared the current inside the tungsten telluride and the current inside the gold contact. It becomes higher in the center and avoiding the edges on the sides.
Can you also image along the wire direction, not just a cut? Why are you showing one cut and not, for example, an image of the entire wire?
I can do that, but it's just going to be boring. It's infinite channel.
So it will be the same cut for any cut on the gold, and then what happens at the transition between gold and the tungsten telluride?
In fact, we are measuring away from the gold because if you think about it, there's going to be some weird stuff going on the connection between the gold and the tungsten telluride.
How can I rule out that this is not some sort of thermal expansion of this bar? Or
no, but
just some sort of structural change that changes the profile.
Yeah. Yeah. So for that, I have the next one. So if that was as you were saying, because of thermal expansion or something like that, it should be monotonic. Yeah, so if you go to lower temperature, it should stay the same direction.
Well, it depends how it depends how the thermal expansion.
Yeah, I agree. But it's kind of introducing a very complicated model for maybe I don't know, but yeah, this is what we saw. We saw that when you when you scan at the function of temperature, it first goes up in 20 Kelvin and then goes down again in 5 Kelvin. So it's non-monotonic in that sense.
Okay.
And now if you go back to the 2D plot, it's kind of more clear. If you look on the center here, you have a peak on magnetic field between 20 to 10 Kelvin, and also the profile is the nearest around the same temperatures. Yeah. So it's
you have a similar plot for the gold.
Again?
You have also a similar plot for the temperature dependence of the profile of the current in the gold part?
Yeah, but it's the same. Yeah. Yeah.
So it will not change the temperature?
No, not at all. Yeah.
Okay, good.
You said before you have to invert the BO-Savar to get the currents. So how would the currents look like? They're not necessarily simple functions of the magnetic field, right?
Yeah, it's not as simple. And in fact, as I will show later on, we're fitting. So what we do the opposite. We did the opposite. We didn't do like reverse engineering of the current. What we did is we got the whole phase diagram, and we tried to get the best fit between the profiles that would generate from BO-Savar law to the profiles that we measure, and from that we were trying to fit the best profile fit.
Okay, because you said before that the integral has to be the same, but I'm not sure why the integral of the magnetic field has to be a constant. Should be the integral of the current is a constant. You're saying.
Yeah, but the magnetic field in the x direction is going to be. Well,
it depends where you're measuring the magnetic field also, right?
Yeah. No, but it is, I think. So it is, I think, true that the magnetic field will be the same integral. But it is. This is what we measure.
Okay.
Yeah. So in order to understand all of that, and
I have a small question.
Yeah.
About meaning, how come that most of the current wouldn't go through the gold? Meaning, there's a big difference in resistance between the gold and your material, the 2D material. So most of the current should go through the gold.
Yeah, but it's just 2 ports. Let's go back. You just flow current from here to here. So it's the same current. Like maybe I missed the question. Misunderstood the question.
Okay, I understand. Maybe later on. Okay, thank you.
Yeah. Okay. So yeah. So in order to understand all of that, what we did is we used ab initio calculation, first principle calculation based on the lattice of tungsten and telluride, and from that we got the 2 kind of interactions in the system: the momentum relaxing interaction and the momentum conserving interaction. Now, as I was saying before, in the momentum relaxing interaction, we have 2 kinds of interaction: interaction with electron and phonon. So here we parameterize this interaction rate with mean free path, which is the distance that electrons travels between successive interactions with phonons, and we have also interaction with impurities. And what we want to get is like the total momentum relaxing interaction, and you get this kind of curve. And you sum them both, the interaction with phonon and interaction with impurities, where at high temperature, the main source or the main interaction source is with phonons, and at low temperature, the electrons mainly interact with impurities. So what about the interactions with between electrons themselves? So if you take into account just the Coulomb interaction, so as I was saying before, so this is this curve. As I was saying before, this is very weak in this material, and it's about 2 orders of magnitude weaker than the momentum relaxing interaction. This is unlikely that the interaction in this system or the hydrodynamic effect in this system has to do with Coulomb interaction. So again, it's unclear what's going on in the system. So in order to understand that, we took a closer look on what's going on with this interaction with phonons. So if you look on this interaction, electron and phonon, and if this phonon is long-lived enough, and since the sound velocity, the velocity in which this electron, the phonon travels is much smaller, much lower than the Fermi velocity, there is a chance that a lot of electrons will meet this phonon, and one of them will absorb this, will be absorbed by another electron. So in fact, what you have here is interaction between electrons that is mediated by phonons. So this is not a new interaction. You know this interaction from BCS theory. This is the kind of interaction that bind 2 electrons to form a Cooper pair. And if you take this interaction into account, you find that there is a region here where this interaction is actually more rapid or more fast than the interaction between the electrons and the lattice. And actually what
is the blue line?
So the blue line is the momentum relaxing interaction, both the phonons and the impurity.
But what about Coulomb scattering? I thought the Coulomb scattering should usually gives you a much faster time scale than for relaxation and
yeah, you are a bit,
phonon.
You're a bit
you think that the Coulomb?
Yeah. So this is.
You think that Coulomb gives you a longer mean free path?
So this is calculated. So they calculated it to 0 T0 temperature, and then just using Fermi liquid, they just at T squared, they just put here, extrapolate from zero temperature. It seems to be very low. This is the idea.
Who's that? Okay. Who is they? By the way,
It's a DFT group here in Harvard. Vinay Narang. Yeah. So so what you see here is that there is a region where this interaction between electrons is more rapid than the interaction with the lattice, and it seems like it's kind of the same range of temperatures that we have the hydrodynamic effects. But as I was saying before, what we can do even like we can do more. We can just calculate what will be the current profiles inside a channel for different momentum relaxing and momentum conserving min-phi paths. And this is what you see here. There's kind of a phase diagram of the current profiles inside a channel, depending on the momentum conserving min-phi path in x-axis and the momentum relaxing min-phi path in y-axis. And the color here represent how non-ohmic is the current. Okay, so 0 here represent completely flat currents, and 1 here represent completely parabolic or completely Poisson flow, or hydrodynamic flow. And you can see here different regions. You have the ohmic region where the momentum relaxing interaction is the fastest. You have the ballistic region where both the momentum relaxing min-phi path and the momentum conserving min-phi path is longer than the width of the sample. And you have the hydrodynamic region where the most or the fastest interaction is interaction between the electrons. And now what we can do is to use the theoretical results that we got from the ab initio calculation. And this is going to create a path in this phase diagram. And together with that, we also have our profiles that we got from the experiment, and we can just fit those profiles that we got from the Boltzmann transport equation. And this is what we got. Okay, so you see, this is the path that we get from the theory, the first principle theory. And those are the measurement points. Fit between the measurement points and the profile that we got from Boltzmann equation. So you see, it's kind of on the edge of the hydrodynamic region, and it's kind of follow the same trend, the theory and the experiment. And if you just take the profile that we got from the theory and compare them the profile that we got from experiment, this is what you get.
Can you go back to the theory? Okay, sorry, just finish the slide and go back to the theory plot.
Yeah.
The one where you're showing the timescales. So it seems like, you know, the momentum relaxing timescale, you know, it depends on the number of impurities, the density of impurities. It looks like it has to be super fine-tuned. You know, what you're showing, the red plot is just depends on the phonon band structure. And
so it actually do not depend so strongly on the I can show you, but it actually does not depend so strongly on the impurity level. In a sense that this, so the main finding, the main fit between the theory and the experiment is the fact that in both of them you will see a peak in magnetic field at around the same temperatures. This is kind of,
to find that the theory fits the experiment doesn't mean that it's wrong. But if you go back to that slide, it looks like, you know, you super fine-tuned. If you had a slightly stronger disorder, you'd be there's no hydrodynamics.
Yeah, it's true. So we know that the bulk material has disorder of few. It's actually larger. It's about 10 microns. And in fact, this line is very close to the size of the sample. So we don't know. It's very hard to know if there is impurities that is purity length that is larger than the width of the sample, because this is when we start to fill the edges.
Did you just have one sample, or did you try several samples?
Several samples. When you take much wider sample, you don't see this effect. This is kind of
much wider.
The effect is very, yeah.
Why does it again depend on the width of the sample?
No, because you need the momentum relaxing interaction to be, in order to get kind of reasonable change in the current, you need the momentum relaxing interaction to be on the order of the size of the sample. Otherwise, you are going to be somewhere here. Somewhere here.
Well, I'm just trying to understand why does it depend on the width of the sample? What's the relation?
No, it's just how the profile will look like.
Mm-hmm. Oh, you're saying you get.
So this is normalized to the width of the sample. So the wider your sample, the more you are going to be pushed to the black region here.
I see.
Like you confine it in the specific geometry, and what is competing here is the momentum relaxing mean-free path and the momentum conserving mean-free path, and both with respect to the width of the sample. So if the sample is much wider than those dimensions, you won't see the effect. You won't see the change, because all happens in much shorter length scale than the width of the sample. So it won't affect the profile.
Mm-hmm. I mean, can you somehow, I don't know, try a different sample with different resistivity, somehow change the disorder strength to see whether.
Yeah. This also we didn't do it in purpose, but we had like two sets of samples, one more like purer than the other, and we got also better results in the purer sample. Yeah, this definitely happened also. Yeah.
Okay.
Yeah. So yeah, as I was saying before, the main finding here is the fact that we got we reproduced the non-monotonicity from theory, and we got a peak at around the same temperatures that we got a peak from experiments. And we think it's kind of proved that indeed this model kind of captures the way the electrons interact in the system, and it kind of shows that indeed the interaction is not probably Coulomb interaction, but rather interaction that mediated by phonons. And this, as I was saying before, may open the way to combining hydrodynamic with many other properties that are available in those semi-metals. For instance, even tungsten telluride itself, it is non-isotropic material. So we were using a specific direction of the crystal. But our prediction that if you kind of create a specific geometry, you can combine different direction and get all sort of extremely non-trivial current profiles. Yeah, so just to conclude, we were using an extremely sensitive magnetometer together with very high resolution to show that the current inside tungsten telluride is hydrodynamic, and that this hydrodynamic effect depends strongly on temperature. It's non-monotonic on temperature. And by comparing those results to a theory, we found out that the origin for those hydrodynamic effects are not probably Coulomb interaction, but rather interaction between electrons that is mediated by phonons. And that's it. Just to thank all the people that worked together with me to get those nice results. Thank you.
Thank you very much. So I have a question. So, okay, I don't know, maybe I can ask many, so maybe other people want to ask. I can wait.
So what's the size of the Fermi surface in these materials? relative to the Brilliant Zone. Huh?
Yeah, so it's not very large because it has both electrons and holes. It's a compensated semi-metals. This we think we know because when you try to measure hole voltage, this is almost zero. So it means that it's the number of electrons in hole are almost the same. So you have two kind of you have pockets of electrons and holes together.
And is the resistivity extremely low, or is it?
It is very low. Yeah.
What?
Yeah. It's hard to say in our samples, but in other similar samples, because we were trying to do it in a very simple geometry, so it won't affect the flow pattern. But in order to measure really nicely the resistivity, you need to do 4 probe and stuff like that. But in other samples that we made, we got extremely low resistivity at low temperatures. Yeah. It's kind of a similar effect. When you go to a very low temperature, the momentum relaxing interaction drops dramatically, and then you get very low resistivity. Yeah.
Right. So this is a condition that is usually necessary for an effect called phonon drag, where the electrons' motion actually drag the phonons with them. Did you think maybe there's a way to see the phonon drag?
So yes, so actually yeah. So it's actually interesting in the next lab to us, they were measuring the phonon drag in graphene using, again, NV Center by looking on the noise that those phonons generate. So it's in graphene they generate. So it probably depends on the sound velocity and the size of the sample, because what happens is when it hits the edge of the sample, it generates a lot of noise. And in principle, yeah, if you measure this noise, and in fact, the fact that NV Center is a qubit also allows us to measure noise in a gigahertz range. So it is possible to measure also this effect, yeah. And it was measured in graphene, but not in this material, yeah.
Okay, thank you.
Other questions? So I can ask a question. Oh, go ahead.
Well, I have one question, which is, I mean, did you think about using different geometries, like looking at, for example, if your channel were to suddenly become much wider suddenly, then you could even get like eddies and stuff like that. Did you look into that at all?
Yeah. So we thought about it, but so at the beginning we were trying to do exactly that, but then we say, okay, we don't understand what's going on. Let's start with the simplest, and then we go beyond that and try to look on more complicated geometry. Yeah, but definitely this is going to be extremely interesting, and together with the fact that it's non-isotropic. So when it moves to the sides, it has different resistance, so different viscosity, and this can give very non-trivial behaviors. Yeah.
So I have a question. So I mean, it's not a really technical question, but what's your motivation for studying this viscous flows? I mean, I could go down to my kitchen and pour some oil.
So yeah. so I think so. So different aspect. I think one is first. It's kind of interesting to get a non-trivial flow of electrons. This is about the electrons, not about hydrodynamics. But you can also get situations like the one that I just mentioned, the fact that you can get a fluid that is anisotropic is kind of hard to get in your kitchen, and it seems to be possible to get in those materials. So you can probe hydrodynamic in a way that is probably not very possible in other systems.
I mean, liquid
But you can also think of how to combine, I don't know, hydrodynamic with other things. For instance, this is very low temperature for hydrodynamic. In graphene, for instance, you get hydrodynamic in about 100 Kelvin. So this is already very, very low. So it seems like you already can. It's possible to combine this with superconductivity, for instance, or stuff like that. Yeah. So I don't know. So it's kind of opening kind of interesting. It's an interesting way to combine hydrodynamic with other properties, I think.
Mm-hmm.
This is, yeah.
And what's the motivation of doing this in this specific material?
So, so this is related to the idea that this material have predicted to be wild, type 2 wild semi-metal. And there are predictions that when you have wild semi-metal together with hydrodynamic, you should expect to get some the Planckian limit of energy dissipation and stuff like that. In fact, we kind of suspect that our measurements also show that this is not wild semi-metal. Because if you calculate using the same calculation I've shown, you from first principle you can change. So you can calculate what will happen if it's indeed wild, if it's not wild, and you get different. You will get different temperatures in which this peak happens.
Mm.
In fact, so we kind of think that it's actually not wild semi-metal. Maybe, I don't know.
It doesn't.
But this is what was the first motivation, the fact that it's wild semi-metal. And yeah.
Mm-hmm. I mean, it could be that it's just doped. That it's doped wild semi-metal, doped enough that you don't.
It seems like it's not very much doped, as I was saying before, because when we measure the hole voltage, it's almost zero. And you have also very high magnetic resistance, which has to do with the same effect, the fact that you have almost the same number of electrons and holes. So we think it's very close to, I don't know, charge neutrality or something like that, because it's kind of, you have a lot of electrons and not of holes, but the same number. So almost compensating.
Mm-hmm.
Yeah.
Okay. Mm-hmm. טוב, Assaf?
No, I have no more questions, but people are going to talk to you more on the Zoom, so we can just thank the speaker again. And
yeah, thank you very much.
תשתנה, אני קצת רוצה לדבר איתך עוד, אבל אנחנו יכולים, everybody can retire.
תודה רבה.
Thank you.
תודה.
תודה, להתראות.
ביי, אסף, תודה רבה, אנחנו ניפגש.